Have you ever pulled a suitcase at an angle across the airport floor? Even though you're pulling in a diagonal direction, part of your effort goes horizontally to move it, while part lifts it slightly off the floor. That's resolution of vectors in real life. Hello learners! In today's session, we'll discover how any vector, say force or velocity, can be split or resolved into two parts along desired directions. This process helps us break complex, multidirectional vectors into simpler, one-directional components, usually along the x and y axis. This is especially helpful in situations involving inclined planes, projectile motion, or forces at angles. As you see in the diagram, vector A can be split into two component vectors, one along vector A and one along vector B, forming a neat triangle or parallelogram setup. Now let's dive into how we express vectors in component form. Imagine a vector A. We split it into two parts, one along the x-axis and the other along the y-axis. We write it as A equals A sub x times I hat plus A sub y times j hat. Another vector B would be written as B equals B sub x times I hat plus B sub y times j hat. To add them, we simply add corresponding components R equals open parenthesis A sub x plus B sub x close parenthesis times I hat plus open parenthesis A sub y plus B sub y close parenthesis times j hat. So we define R sub x equals A sub x plus B sub x and R sub y equals A sub y plus B sub y. This method turns vector addition into simple arithmetic, and yes, it even extends to 3 dimensions using the k-hat for the z-axis. Once we know the horizontal and vertical components of a vector, R sub x and R sub y, we can calculate the overall or resultant vector. The magnitude of the resultant vector is found using the Pythagorean theorem, R equals the square root of R sub x squared plus R sub y squared. To find the direction of this vector, we use the angle theta. Theta is equal to the inverse tangent of R sub y divided by R sub x. These formulas help us take two separate components and combine them into a single vector with both magnitude and direction. This approach is especially useful when dealing with motion, forces, or fields acting in different directions. When two vectors, A and B, are not perpendicular and there's an angle theta between them, we use the law of cosines to find the magnitude of the resultant vector. The formula is R equals the square root of A squared plus B squared plus 2 up times cosine theta. This method is especially helpful when vectors aren't aligned along the x or y axis. To determine the direction of the resultant, we use the law of sines, which states R over sine alpha equals B over sine beta equals A over sine theta. These analytical laws are powerful tools when solving problems involving forced triangles, inclined motion, or vector navigation. What if your problem isn't confined to a flat surface? No worries, we've got 3D vector addition too. In 3 dimensions, a vector becomes A equals A xi cap plus A yj cap plus A zk cap. To add two vectors A and B, we simply add each component R equals open bracket A x plus B x close bracket I cap plus open bracket A y plus B y close bracket j cap plus open bracket A z plus B z close bracket k cap. And what if there are more than two vectors? Just continue adding, component by component. For example, Tx equals Ax plus Bx minus Cx, and similarly for the y and z parts. This technique is used everywhere, from analyzing aircraft movement to computing net electric or magnetic fields. Let's apply what we've learned with a practical example. A motorboat is moving due north at 25 km per hour and the water current flows at 10 km per hour 60 degrees east of south. The angle between the two vectors is 120 degrees. We use the law of cosines to find the resultant velocity, r equals square root of open bracket 25 squared plus 10 squared plus 2 into 25 into 10 into cosine 120 degrees close bracket. This gives us approximately 21.8 kilometers per hour. Now for the direction, we apply the law of sines. Phi equals sine inverse of open bracket 10 into sine 120 degrees close bracket divided by 21.8, which gives us an angle of approximately 23.4 degrees east of north. Let's quickly revise what we've learned about the analytical method of vector addition. First, we learned that breaking vectors into components along x, y, and even z directions gives us mathematical precision. Then, we saw how to calculate the resultant's magnitude using the square root of the sum of squares and its direction using inverse tangent. We explored cases where vectors are at arbitrary angles using the law of cosines and law of sines. Finally, we applied everything to a real-world example involving a boat in a flowing river just to prove how powerful this method really is. So the next time you encounter forces, displacements, or velocities acting at different angles, remember, the analytical method turns arrows into answers. I hope now you understand how resolving and recombining vectors forms the backbone of motion analysis. See you in the next session with another exciting concept of physics.